So what I want to really present today is sort of an overview of the strategy that we're employing in RISE 2 on how to develop the next generation understanding of lunar dust toxicity. This is, of course, particularly important now because of the commitment for manned exploration of the moon towards the eventual goal, of course, of a surface outpost. So there is something that we do know about lunar dust toxicity, and in fact, it was implemented for Artemis 1, so phase 1 of the Artemis mission, and it was based on the Lunar Airborne Dust Toxicity Assessment Group study, and that allowed the development of sort of permissible exposure limit. And this was based, however, on primarily rat inhalation exposure studies. And rat inhalation exposure studies are important, but what we believe very strongly, if we're going to move into the next generation of long-term human presence on the moon, is that we need to understand more about the toxicological hazard of respirable lunar dust. So we've been focusing on using a variety of biological techniques. Of course, the time-honored rat and mouse inhalation studies, recent results from the workshop on lunar dust in February of this year that suggested that perhaps mouse inhalation studies are better than the use of rats. But again, we are working on this and developing an inhalation chamber over the next year. The second thing that we've been working on, particularly with graduate student Jamie Chang, is exposure of human lung cells to lunar dust simulants. And this takes on a variety of directions. We've been looking at pulmonary cell viability after exposure, genotoxicity of both mitochondrial DNA damage and nuclear DNA damage, as well as mitochondrial reactive oxygen species level, which indicates mitochondrial dysfunction. And again, there's been recent discussion of the results of these experiments earlier this year. The other thing that we're working on, and the next talk is going to focus on the work by graduate student Donald Hendricks, is on the effect of minerals on OH radical production, which of course is known to cause a variety of inflammatory processes in the lungs. And for this, we're using a variety of available simulants in aqueous media, but also in this region, we're looking at ways to modify these available simulants. And these simulants are good because they're available in quantity that we need for these toxicology studies. But we're interested also in the kind of modifications that would make these simulants more relevant to the lunar surface and new simulants that capture some of the other toxic components of lunar dust. So we are interested in not only in diverse approaches to studying toxicology, but also in diverse lunar materials and analogs. Because what our strategy is to try to identify the most toxic components of lunar finds, which in turn will allow us more predictive capabilities as we move to different portions of the moon for our manned expeditions. And of course, part of this is what controls our toxicity, which helps us understand predictive information. So if we look at lunar finds, everyone knows that the primary constituents of lunar finds are the rock-forming silicates, minerals, as well as the volcanic and impact melt glasses. And many of these, of course, are concentrated in different parts of the regolith by the comminution of rocks, by meteorite and large and small impacts. And this is just a slide that was borrowed from Schrader et al., which was a very nice depiction of the fact that the lunar finds in the regolith have a different composition. So if the bulk regolith is shown here by this horizontal line, there is a different abundance of these silicate particles in the finds, which of course will contribute to the inhalation hazard. So how well do we actually know the effect of these silicate dust components? Well, we thought we knew a fair bit because we thought olivine was olivine as an example, but I don't want to steal Donald's thunder at the next talk, but just to suffice it to say that when we even look at something simple as olivine, there is a strong difference in composition, and that is how it relates to OH generation. So clearly we still need to look at the relative toxicity of mineral and glass component of lunar finds. The next thing that we have to be aware of in lunar finds is the presence of the agglutinates, these glass solid particle composites. And so we need to have a fair amount of these available to look at their toxicity. So we've been exploring mechanisms where we can actually generate our own agglutinates. So here's an example of what we have done by roasting JSC1A, shown here on the left, ground original, roasting in hydrogen at 900 degrees. And these are both at the same scale. This is 1 micron bar here and here. And what you can immediately see is that some of the larger particles are still retained, but we have made a very different texture, one that has a highly sintered texture, with enough structural integrity to support these elevated regions, these spires. And we were just in the process of looking to see if we indeed were able to make the glass in this process that we need when our analytical facilities were shut down due to COVID-19. But we will continue working on this. The important thing that we have been able to ascertain already is that this reduced material, in addition to the starting material, does affect human lung epithelial cell viability and cellular DNA damage. And this reduced material that you just saw results in a significant decrease in cell viability and increase in DNA damage. So basically what it's saying is that as we're producing material that is more relevant to the lunar surface, we may find a change in toxicity level that's important for us to understand. Another direction that we're working on, which is actually quite important also and has been undervalued, is the presence of sublimates in the lunar finds. So we all know about the lunar orange soil. We know about the presence of these glass beads and the presence of sublimate coatings on these beads. Now, these sublimate coatings are very friable and have contributed to the respirable fraction in these soils. And importantly, they include a variety of sulfides, fluorides, halide salts. And you can see a variety of elements here with a variety of toxicity that we need to understand what role these might play when the astronauts are exposed to these dusts. The other thing that we've realized now is that the sublimate coatings change upon exposure to the surface of the moon, and we need to know what happens to these in terms of if we're producing a variety of metals and lose the coordinating ligands, the fluoride and the chlorides, and sulfides, does this render this material more or less toxic? So this is actually a real problem because, again, we need to know what are these sublimates and what are their stabilities. So we have turned to experimentation as part of our efforts through RISE-2, and that is if we actually take lunar magma and allow it to boil using the volatile saturated materials that we can generate in the lab at given low FO2s, what are the nature of the gases that are escaping from this? And most importantly, what sublimates, what crystalline material do they produce? And how stable is this crystalline material? So to give you an example of the kinds of materials that we can produce through these experiments, here is an example. This was actually from Mars.
8 minutes.
Thank you. But you can see here what this does for us. This is just an example of an evacuated silica tube in which we've allowed Martian basalt that was doped with a variety of volatiles to boil. And in the process of boiling in a strong thermal gradient, we were able to trap a variety of sublimates. And shown here is an example of the sublimates that we can see quite clearly. We have, for example, maghemite. We won't expect this on the moon, but it really just shows that we get nice sized particles that can be analyzed. In the case for Mars, it's this maghemite is adhered to the surface by mollicite, which is an iron chloride, and above it is a zone of massive sulfides. But what this is showing on the right here is that by using SEM, and we're also going to be using the XRF and TES beamlines at Brookhaven National Lab, NSLS2, we can see that we would be able to identify the nature of these sublimates. Here, for example, is a beautiful crystal of pyrrhotite, vapor deposited pyrrhotite. And then we can then go and buy some of this material once we know what it is that we produced, for example, lead sulfide or lead chloride, buy them off the shelf and subject them to space weathering, analyze the product of that, and then add that to our toxicity studies. So what this has allowed us to do is to add experimental work into our analytical work on trying to figure out what exactly are the toxic material parts of the lunar finds. So in summary, what we want to be able to look at is to assess the toxicological hazard of respirable finds based on a variety of biological techniques through the Stony Brook School of Medicine as well as look at diverse lunar materials and analogs that we have made and analyzed so that we have a better idea of what it is that we are subjecting our toxicological studies to in more detail. So I want to thank you at this point and open up for questions.
Thank you, Hannah. Do we have time for questions, Aisha?
We do have time for questions. So if there's anything in the chat.
I don't see anything in the chat. And nobody's raising the hand yet.
Oh, there is a question in the chat. Paul Fund has asked, why do they need to be below 5 microns?
Okay, that's a great question. And this was actually brought up extensively in the Lunar Dust Workshop in February by the people who are working on these things in medical school. And basically the thought is that the 5 micron size is the particle size that goes most deeply into the lungs, and therefore has a much tougher time coming out. And therefore, as it sits there, there's a greater chance of inducing inflammation and other problems. The larger particles can be readily coughed out, and therefore they are not remaining within the lung pockets for as long.
There is another question. Lon Creel is asking, shouldn't we be looking at isolating the crews from all of these questions about effects on their well-being?
Exactly. We certainly would like to be able to do so. And that's, for Artemis 1, the goal was, what is the minimum grain size that we have to worry about, because we would like to essentially not worry about it, to be able to avoid inhalation hazards. And that's ultimately the goal we want, but we also need to set standards. So to what extent is the toxicity such that an X amount of exposure per day is permissible? So, yes, ultimately we would like to not expose them at all, but realistically speaking, we need to develop the technology for a permissible load.
Great. Okay. Thank you, Hannah.